Well, good afternoon. Okay, this is the wrong slide. The last time we talked about equilibrium, and we discussed several equilibria, and we talked about Le Chatelier's principle. And one of the equilibrium we have discussed quite in detail is the dimerization of nitrous oxide to N2O4. Nitrous oxide is brown, N2O4 is colorless. And so in equilibrium, you will have some of this and some of this here. The equilibrium constant is 6.87. That means, as we say very slang-like in chemistry, chemical slang, the equilibrium is on the right side, okay? The equilibrium is on the right side. That's how K is larger than 1. And that means you have this is in the numerator, and this is in the denominator. So you have this here divided by the square of this here. That means you're going towards products. This is why K, this is larger. K is larger than 1. K is 7. Now, just from looking at these two pictures here, you can tell two things. First of all, you can tell the change of standard enthalpy at standard condition. What would that be here? How do you do that? So you have a monomer, 1 NO2, and you need 2 to form N2O4. What would be the change of delta H? Of course, it's written here, but what would it be? It would be exothermic. And why? Because you're forming bonds. You take two monomers and bond them together to make one dimer. That's the first thing. The second thing is, what is the change in the entropy? Does it get larger or smaller if you go from left to right? It gets smaller. The entropy decreases because you have less microstates here than here, okay? So with this, you already know that this is an exothermic reaction, and it's minus 57.2 kilojoules per mole, and it has a K larger than 1. That means it goes into that direction in terms of the equilibrium. So we say leisurely the equilibrium is on the right side, it's on the product side, okay? That's what you want to do. You want to dimerize NO2 to make N2O4. So you hope that this reaction goes that way. What would be the delta G for that to be spontaneous? The delta G at standard conditions would be negative, okay? Would be negative, excellent. So we then talked about Le Chatelier's principle, and Le Chatelier's principle is nothing but the fact that you subject a system to stress, that it will react in a direction to reduce that stress. So what would that mean? If I put some more NO2 in here, what will happen? What will the system do? What will the equilibrium do? If I put more NO2 in here, am I in equilibrium at that point? I put that NO2 in there? No. So I can make a reaction quotient. The reaction quotient would be this here divided by this here. And since I increase that here, that means Q would be larger or smaller than K? Smaller than K, exactly. Oh, you're getting the hang of it. That's wonderful. Okay, so in order to get Q equals K again, it has to make more product that you get back to the equilibrium constant, that you get back in equilibrium. So if we add reactants, you bring it out of equilibrium, and it needs to get back into equilibrium, so it will make more products. Now let's add products. What will happen? You are out of equilibrium. The moment you add products, you're out of equilibrium. So what will happen? So Q is what? You're adding something here. So Q is larger than K, much larger than K. So what will happen? It will go to the left. So it will make reactants until you have the condition of K reached again. All right, now you understand the difference between Q and K. Now we also talked about heat. If it's exothermic, we look at heat as a product. So if I have an exothermic reaction, that would be an exothermic reaction. That means I have plus delta E. That's the heat that I release here, okay? So now I increase the temperature. So heat released, and obviously I increase, heat is one of the products. I increase one of the products, that's the heat. Which direction do I drive the equilibrium? I drive it to the left. I'm making more reactants, okay? Now, if it's endothermic, heat would be a reactant. If I increase the temperature and it's endothermic, then I drive it to the right side. That means I make more products, okay? Good. And this was one of the problems with the Fritz Haber invented this synthesis of NH3, and they use a catalyst in order to get the activation energy down, but they cannot get it down that there's no activation barrier. So one of the conditions is if you increase the pressure, so we're changing the reactants, you increase the pressure, you push the equilibrium towards the right side, okay? If you increase the pressure, what would that mean for Q? Q would become smaller than K or larger than K? So I increase this here, okay, it becomes smaller than K. So in order to get K, I need to make more products to get back to K, right? So this is one of the things. So in order to get a good yield, you increase the pressure of nitrogen gas and hydrogen gas to make ammonia. Ammonia can be used as fertilizer and for other non-peaceful purposes. And if you go, but this is an exothermic reaction. So if you also increase the heat, the temperature, what happens? You go to where? You go to the left. Clear? Hello. you go to the left. So this is a product here. And so I increase the temperature, I'm putting in more product, so I go to the left. What would this, if I increase the heat and it's not in equilibrium, would be Q would be larger or smaller than K? Larger, exactly. Oh, good. So you have to find a compromise between temperature and pressure here in order to get the optimum yield. And with this, the actual conditions was at 500 degrees Celsius and at 200 atmospheres, and this guy, Robert Bosch, he's the guy who makes you wiper blades and all kinds of car electric stuff. You've probably seen this, Robert Bosch, many times in your cars. He then made in 1940, he changed the catalyst and made it really work very well so that it could be used for some non-peaceful usage, okay? And then we have talked about multiple equilibria. We know the equilibrium constant for an equilibrium between A and B, and we know the heat of reaction, the change in the heat of reaction. So we know also from B to C, we know the equilibrium constant, the heat of reaction, we call this delta H2, this change in heat of reaction, or the heat of reaction. And then we can also go from A to C, that's the third heat of reaction, and equilibrium between A and C. So now I want to express K3, that's that equilibrium constant, in terms of the concentration of this divided by the concentration of A, so this would be this. But I know that C is also C over B, okay, that's this here, and A is, and B is B over A, so I put this in here, so this is equivalent to this here. Now with this, I have this and that constant in there. K3 is K1 times K1 times K2. And with this, you have K3, okay? So, and the heat of reaction, for that equilibrium here, would be the change of enthalpy for this equilibrium plus the change of enthalpy for this equilibrium, okay? So this is a multiple equilibria. So today, we're going to connect the free energy and the equilibrium constant. So we talk further about equilibria, and we will look at reaction A moles A plus B moles B gives C moles C plus D moles D. So these are our products, and these are our reactants. And we've done this now many times. In order to go spontaneous from left to right, we have to have the delta G at standard conditions. Standard condition is 1 atmosphere in gas, or if you have gases, or 1 mole on each of your reaction partners and your products. This would be standard conditions, all right? And these standard conditions, of course, are conditions for us just to see which way it's going to go. So you won't have very often at all a case where you have everything is at 1 mole on the left side, everything is at 1 mole on the right side, or at 1 atmosphere on the left side and 1 atmosphere of the right side. This is our state, our standard condition state, and that's where we compare. And when we calculate that, if delta G is smaller than 0, that reaction will be spontaneous. Do you agree with me? Goes from the left to the right as I have written it, okay? And what will happen to K? For K, obviously we want a spontaneous reaction, so we want to make products. So the products are in the numerator for the reaction quotient. So the numerator divided by the denominator, what would that give? K would be then, no, K is not 1. K is a constant. K is a constant for at that temperature. And that has to be larger than 1, okay? It can be anything depends how well this reaction goes. It can be 10 to the 13 for many reactions, 10 to the 13, 10 to the second, and so on, okay? It's larger than 1, K larger than 1. Delta G is smaller than 1 at standard state, and with this K is larger because you're making products, okay? So this would be the condition for spontaneous reactions. Now let's look at this. We have delta G at standard conditions. The free energy at standard conditions is larger than 0. Larger than 0, what does that mean? Is the reaction spontaneous or not? Non-spontaneous. So we write it this way, we know it's not going to go in this direction. And that means it will stay here. And with this, if you make your reaction quotient, if you take this, so it's this over that, and if we have more of this here, what would be K? Larger or smaller than 0? Smaller than 0, okay? This is exactly what it is. If it's non-spontaneous, the delta G delta G at standard conditions is larger than 0, and the K is smaller than 0, so you're not spontaneous. Any non-spontaneous reaction has a K smaller than 0, alrighty? So what does this mean? So we have our equilibrium, now we speak slang again. Our equilibrium is on the left side, okay? The equilibrium is on the left side. That means we have lots of reactants that don't want to become products, okay? So there is one case, and somebody said K would be 1. Actually, when would K be 1? If delta G naught equals 0, delta G naught equals 0, then you would have K1, all right? Because this would be 1 and this would be 1, so this would be the same here. With this, you're at 1 atmosphere or 1 mole on both sides. That's a very, very unlikely condition that you would have a reaction that would be in equilibrium. We have the reactants all at 1 atmosphere and the products all in 1 atmosphere, or you have the reactants all at 1 mole and the products in 1 mole. That's a very, very unlikely condition, okay? This condition hardly ever will happen. Delta G not equals 0 and K equals 1. It hardly ever will happen. But for completeness, I'm discussing it here. So, now, since some of you are mathematically inclined, not all of you, but some of you are mathematically inclined, and you've seen that there is a relation between delta G naught, the standard free energy, and the equilibrium constant, okay? And this is the relation. Delta G naught is minus R, you know the constant R, T is the temperature, times the natural logarithm of the equilibrium constant. Now, if the equilibrium constant is larger than 1, the natural logarithm will be always positive. Is that right? Okay. Now, if we have the equilibrium, so this will positive, this will be, this is larger than 1, this will be positive, this term here, and this will stay negative. So that means that was this case here. Isn't that right? Delta G will be negative, D naught will be negative, and K will be larger than 1. So now if you have K smaller than 1, what will the sign, if you take the natural logarithm, what will the sign be? Negative. Excellent. So if K is smaller than 1, this will be a negative number. Negative times negative gives positive. That means delta G naught is positive, is larger than 0, and K, as we said, is smaller than 1. This is this relationship. Okay? So now you see this as a mathematical expression. You also can take this to the power of e. So your K is the e to the minus delta G naught divided by RT. So we have tied together now the Gibbs free energy at standard conditions and the equilibrium constant. Okay? You can now calculate an equilibrium constant if you know what delta G naught is. Or vice versa, you do an experiment and you determine the equilibrium constant, and with this you can calculate the delta G naught for the free change of free energy at standard state for that reaction. Good. So we've done that. Why don't we give it a shot here and see how well we are doing? You have delta G naught and K, and we have that reaction here. Water in liquid form goes over into water, is in equilibrium with water in gaseous form at 25 degrees. What is delta G naught and K for that reaction at 25 degrees? So is it A, delta G naught is smaller than 0 and K is larger than 1? B, delta G naught equals 0 and K is smaller than 1, where C, delta G naught is larger than 1, and K is smaller than 1. So it will determine, we wrote it in this direction. Is that really where the reaction goes at 25 degrees Celsius? Why don't you think about this and give me your answer? There is a slight majority, not so slight actually, a pretty big majority who goes with C. Okay. Now, this is water at 25 degrees C. You see any steam? Okay, don't see any steam. Okay, so that would be not standard condition. Standard condition would be just by accident. If I would this at boiling point, 100 degrees, I would have 1 atmosphere of steam above here, okay? And So you also, we have about 1,000 times we have talked about what that equilibrium constant is at 25 degrees C. Who knows what that equilibrium constant is? Say it. 300ths of what? Of what? Potatoes or? Atmospheres. 300ths of an atmosphere, okay? That's the concentration. I didn't mean to embarrass you. I'm sorry. That was, but I couldn't resist, you know. It's you always got to say the dimension with it. 300ths of an atmosphere above. This is 300ths of an atmosphere. With this, your answer is already given, essentially. But you could also think about it. What really happens in terms of delta G naught? So why don't you discuss this with each other and give me an answer? Thank you for helping me with 0.03. I really appreciate it. I'm sorry. It's terrible. You never make fun of your audience, okay? And especially if you get help. And I didn't make fun of you. Okay, I go with C. I agree with you. Now, the first thing you could say, is that thing boiling? That would be would go this direction. Water goes into gaseous form. The liquid form goes into gaseous form. Do you see that happening here? No. So obviously, this is not, the delta G is not a spontaneous reaction, okay? Delta G is non-spontaneous, so it goes in this direction. If you have one atmosphere, it tries to get the pressure down and make water to get down the pressure to get to 0.03 atmosphere. That means you have, with this, you have delta G is then what? Delta G would be larger or smaller? Of course, larger. And K, we know K, this is just the partial pressure of this here, and K would be smaller than 1. And I hope this is the right answer here. Exactly it is. All right, good. This is the right answer. I should know that, all right? So now we know that the change in free energy at standard state is the change in the enthalpy at standard state minus the temperature we add times the change in entropy at standard state. That we know, okay? But we also said here that delta G naught is minus RT ln K. So now, we can combine this now, and we can connect K with delta H and delta S, and T times delta S. Let's do that. Here's our delta, we say minus RT ln K, that was this here. This is our delta G, minus RT ln K, is now delta H naught minus T times delta S naught. So why don't we divide this by minus RT? So we get ln K here. ln K, what do we have here? Minus delta H divided by R divided by T. And this would be plus. And this would be canceling delta S divided by R, okay? So this is that here, ln K, and I took this out here because we want to plot ln K over 1 over T. We want to plot that. And so what is this? This is a linear, it's the equation of a line, essentially. And the equation of a line is y equals m times x. M times x, this is x. M times x is the slope, m is the slope, plus b, and this is the intercept here. So if you look at k for so we plot here ln k over 1 over t. Of course, this is in the old days when they didn't have these TI 5 million calculators. You could do this also now, calculate all this. So, but in the old days, people, actually during my time, you were trying to make straight lines that you can derive this. And with this, you're going to get a very good understanding of the whole process. If you just punch in numbers, you will never see what is going on and the interplay between it. And so if you put ln k over 1 times 1 over t, you get a dependence like this. This for an exothermic reaction. Remember, exothermic reaction, that means heat was a product. Heat was a product. Now we increase the temperature. With this, that would be the temperature and the K. With this, we decrease if we increase the temperature and heat is a product, we decrease K, okay? Because with this, the numerator will become smaller compared to the bottom of that equation. And so if we have this here now, ln k, so what is the slope? The slope is minus delta H over R, okay? And that slope is positive, so that will be minus delta H over R, so that means exothermic. What does that mean? And the delta S, what will be delta S here? Delta S will be the intercept, delta S over R, okay? Now if it's endothermic, heat is a reactant. And with this, the equilibrium constant as a function of temperature will increase, okay? Because we're pushing it over to the other side. And the endothermic reaction would be then ln k, so this would be, what would be this? This is the intercept. It's delta S over R, and this is minus delta H over R, and this is negative, but it's minus, so that means delta H is positive in this case, okay? So you have to, of course, divide it, you take that slope, the slope, and you divide it and multiply it by R, and you have it, okay? So this is a perfect way for linearizing these equations, and you get ln k, and you get delta S and delta H. So wasn't there in lab 8, wasn't there, that's what you did, you were supposed to calculate the entropy, isn't that right? And this is what you use this equation for. This is called the Van't Hoff equation, Van't Hoff equation. And so didn't you determine the equilibrium constant? Did you? In this, you determine at different temperatures, didn't you do that? And then you plotted it, and from this now, you can extract delta S, the change in entropy, and the change in enthalpy for that reaction at standard state. Now, you were always wondering, of course you're always wondering, why is that? Or why are we talking about this? Nearly everything I say, you will probably ask, why is he talking about this, okay? And so you are saying, and the reason is this, now you can, it's the first time I can give you direct access to the entropy, the change in entropy of a system, okay? And this is what you do, and this is why your lab number 8 is due tomorrow, it's true? Was due yesterday? The guys in the morning obviously go later. They told me it's tomorrow, okay? So some of you had to read the book, and some of you got it from me, all right? Good, but I actually, the GSI or the TA should have also be able to tell you that. But now you know it, so it's not totally parallel, but I do my best. Sometimes best is not good enough. So now we can look at a couple of cases where we look at ln k here, we have discussed this here, over 1 over t, and we look at delta G is H minus T times delta S. Yeah, okay. So delta G, so we're comparing this now, okay? Well, what did we compare here? Let's see. Yeah, okay, we didn't compare anything. So delta G is delta H minus T times delta S, all right? So if I have would it be endothermic? Oh, it says right there. It says endothermic. That means that the slope is minus delta S. Is that right? The slope is minus delta S. And delta H would be positive. That would be here. That would be the intercept. Okay? So this is the intercept, and the slope is minus delta S. And if I have ln k over 1 over t, then I get here, what is that here? My slope is minus delta H over R, delta H not over R, and the intercept would be delta S over R, okay? Intercept is delta S over R, and the slope is minus delta H over R. So if I give you something like this, you will be able to calculate this. So there's now all kinds of cases we can discuss. For example, we have delta H positive, and delta S negative. Delta H positive, that would be this one here, so it has to be somewhere here. And if delta S is negative, what would be the slope, negative or positive? Positive, right there, okay? And if we plot this as ln k, what would be that? Delta S would be positive, would be negative, so it's got to start here somewhere. This is delta S, got to start here somewhere. And what would be the slope? The slope would be negative? Okay. Yes, that's right. The slope is negative. All right, this would be this case. Now we have the case here that's at all temperatures. Delta H is negative and delta H is negative. Delta H is negative and delta S is negative. It goes like this here. And this one, delta S is negative. That would be here. And delta H is negative, so it would be having a positive slope. It would be going this way. Now you could do this here, and you can do this until the cows come home. No, actually, there's only 4 possibilities. So that would be delta H would be positive, and the slope would be delta S. And this one here, the minus the slope would be delta S. Okay, and this here would be what is that? Ln delta H positive. S is would be here, and delta H would be the slope, negative or positive. Again. Negative, okay, and so this one, this one would be negative and positive. So delta H would be here, and the slope for the delta G, and the slope negative, exactly. And this one here, you have delta S would be positive, would be here, and the slope. That's correct. You got it. All right. I'm very happy to see that. So, you remember when we had CO2? It sublimes. It goes from solid to gas. It jumps the liquid state. Okay, it goes from solid to gas. And I had a piece here, and I was playing air hockey and all kinds of shenanigans I did here. And it was sitting on the top of the desk, and it was going into the gas phase. All right? And obviously, the temperature in the room is enough to get it in the gas phase. Okay? So it needs to pick up energy, obviously. That seems to be an endothermic reaction. And then we had this iodine. I point here because it was standing there. The iodine was that solid, which had that purple-violet gas phase on top of it. And this stayed stable at room temperature. But we had also sublimation of iodine. You go from solid to gas, and you did the same thing with CO2. You went from solid to gas. What do you think the entropy would be for both of them? Okay, that's the first part of the question you have to answer. And the second part is, so you have ln k versus 1 over t. Ln k versus 1 over t is this here. Okay, so what gives you the intercept? This is the intercept, and this will be the slope here. So this is for iodine, okay? And what would be the one if you would put CO2 from the solid to the gas? Would it be A, B, or C? Why don't you think about it and give me your answer? Okay. Now, we go from solid to gas, we sublime. Okay, solid is very ordered process, relatively ordered. Gas is rather disordered, okay? Solid is ordered, gas is disordered. You think there's going to be a big difference between iodine, if you go from iodine solid to iodine gas, or you go from CO2 solid to CO2 gas? You think there's a big difference? Okay. So that leaves two choices now, okay? Now, the other thing is, the heat in this room was enough to drive that CO2 from the solid state to the gas state, all right? So obviously it's the heat of vaporization, isn't that right? So which one do you think has the smaller heat of vaporization? CO2 or iodine? Did the iodine had enough to vaporize totally? Enough? Okay. So the room temperature was enough for the heat in the room was enough for the CO2 to go into the gas phase, but not enough for the iodine. So which one has the smaller heat of vaporization? Okay, why don't you discuss this with each other and give me the right answer, please? Okay, not so vivid discussion here. I can't hear my own word. So what is it? What's going on here? Here it is. I think I go with C. All right, so some of you went in a different direction. So the heat of vaporization, which one is the smaller one? CO2. Okay, CO2 is smaller. Would that be the steeper slope or the flatter slope? Flatter slope, okay? Flatter slope would be this here, okay? And steeper slope would be this. So this is this here. The entropy, we already agreed, there's no big difference, okay? But the enthalpy, which is the enthalpy is minus delta H over R, the less steep the slope is, the smaller the number. And with this, you had, rightfully, some of you selected C or number 3, okay? And you understand that now at least, and this is the good part. So let's have a nice little experiment talking about what's going on here. Anybody see? Ah, here it is, okay. Nope. Control B doesn't work. It's Control B, yeah? No? Why does this not work, B? Okay. If in doubt, do something else. Okay. No, I like to have the full attention, though. Should work. Oh, okay. Never give up, though, but I don't have enough time. So what we have here, we have this beautiful orange compound. Remember, it's orange, not red, okay? Orange compound, beautiful. What is that? Ammonium dichromate. And we're going to react this. Now, what do? You just put fire to it? Okay, so it seems to be maybe if you just can do give it a little activation energy, something must happen. Then, obviously, it is an exothermic reaction. Now, you see that here? So it starts now. Oh, look at this. It's a volcano. It's a little volcano. All by itself. You see that? Oh, my. Oh, see, it's spewing lava. This is how they did special effects in the old days. They have a little chemical, and then they set the camera in there, and there he comes. Godzilla, Godzilla. Special effects, or what's King Kong on the volcano. Can you hear it here? Hear that? That's quite a volcano, huh? Godzilla. So that's how they made these movies. But they didn't show the rim of this here, of course, okay? Okay, so there it is, thank you. Always a nice demonstration of our volcano. They see that we had this little pile of this compound, and now we have all this mess here, all the lava in quotation mark. So what do you think is the change in entropy? Positive or negative? Change in entropy. Look at it. Was that before? Of course, we came in a much more disordered state, many more microstates. So we had a pretty ordered state, and then we came in a disordered state. So what was delta H, you think? Delta H. Was it exothermic? Do you see the flame there? Was exothermic, okay? So delta H was negative and delta S was positive. So this is how you would plot this. If you would have to plot G over T, that would be this here. Or you plot ln K for that reaction, over 1 over T, that would be this here, okay? And so we have seen that we can calculate the direction of a chemical reaction, and of course we have to look how we have written it. We can calculate from the difference in the free energies at standard state. We can calculate. If it's smaller than 0, it goes spontaneously in the direction as it goes, and as we have written it, if it's larger than 0, it stays with the reactants and not with, it doesn't make a product. So now this would be the time 0. Now we let the reaction start, we let the reaction go. And let's see that reaction takes 10 seconds till it's finally in equilibrium. So after 9 seconds, I say, the reactants have a certain free energy, and the reactants have a certain free energy, and the products have a certain free energy. And it's not at standard state, because we let the reaction go. That's still the driving force. And so, and then I look at it again, and I would measure the concentrations at 5 seconds. And I get a different reaction quotient. And then at 7 seconds, I get a different one. I have different delta G's of different free energies of the products and different free energies of the reactants. So the delta G of the reaction at the real condition I'm in, okay, is changing because this free energy and this free energy changes. So if delta G equals smaller than 0, that means Q is smaller than K. And we said this, and in equilibrium, this here, delta G equals 0. And this is what, it's not delta G not equals 0. Delta G equals 0. Somebody said it would be, but K would be 1. But delta G equals 0, okay? It's not, you see, there's no standard state. That's for equilibrium, and with this Q equals K. And if delta G is larger than 0, then your Q is larger than K. So you're more, where are you? More with the Q is larger than K? You're more with the reactants, isn't that right? No, with the product. I'm sorry, you're more with the product. If Q is larger than K. Okay, so this is how you, now this is the, how we call this, the running free energy, the running free energy, and it's not its standard state. And I would like to ask you, no, let's see. So now we have the delta G at standard state, and we have the delta G as it really reacts in the reaction, okay? Standard state, hypothetical, 1 molar each side, 1 atmosphere each side, but now we let it react. So we need to be able to connect this somehow, and delta G of your reaction is the delta G at standard state plus RT ln Q. And this is at any time of your reaction. It can be when you just started or when you go towards equilibrium. Anytime you can take snapshots anytime you want, and it will fulfill that equation because this will express your reaching of equilibrium or how you get towards equilibrium. So delta G equals delta G naught at standard state plus RT ln Q. And what happens if you're in equilibrium? What is delta G then? 0, exactly. All righty, delta G equals delta G naught plus RT ln K equals 0. Okay, that's the equilibrium state then. And with this, I see you, wait, let me say something. We have, I heard there's a midterm, is that correct? Okay, on Monday. And so everything that I talk about in class until Friday, end of class, can be part of the midterm. Anything I talk about on Monday will be not part of the midterm, okay? And there is a review session tomorrow here from 5 to 7 p.m. given by Greg Dellinger, and I will review within lecture the last since the last midterm, the subjects that we have. And I see you on Friday.